Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math basic course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step one aside as we jump into section 6.4 in the Big Ideas Math Integrated Math 1 textbook. This is on solving exponential equations. Now, so far we've done things involving graphing them, exponential growth and decay, and we've compared them to linear equations. And we've solved linear equations in the past. Heck, it was all a part of the first chapter. And, we get x by itself, things like that. This will be slightly different. You can't treat it the exact same way. I think I said at the beginning of this chapter, you really have to kind of reset the way that your mind works with exponential functions. Now that x is in the variable, it's going to be a little bit different what we do. Depends on the problem type where we might get to some parts where we do eventually solve like that, but that's once we get the x down on the ground. When I say down on the ground, remember, it's up in the exponent. It's like 2 to the x power. So some things to note with that, you might need your calculator, or you might need to know some things about certain powers, like what's 4 to the 5th power, some numbers like that. So we'll have to talk about them as we go. We'll see what kinds of examples that they have in the lecture portion, which I'm going to begin with. If you'd like to start with the problem set, jump to the description section down below and find the timestamp to which I start the problems. We go to number 58 here, by the way, and you can also download a PDF of this set as well. I don't believe we're going to need to graph, but we'll see. Without further ado, let's go ahead and get started. We're going to solve exponential equations with the same base. These ones are significantly easier to do, and they'll make sense into what we're going to do when we have unlike bases, or at least what our objective is. Our objective is to get to the same base. That's going to be the idea. And then we will solve by graphing. Okay, I actually didn't know that. But we might use the graphing calculator. Maybe that's it, and that's the difference. So, like I said, I'll let you know if I'm going to attach graph paper down below for you guys as well. Excuse me. The same base versus unlike bases thing, well, let's see what I want to state here. You're going to do this again in IM3. I forget if you do an IM2. I forget. But you're going to do it again in IM3 when you learn logarithms as well, which is the true mathematical way to solve these, especially when you can't make the base the same. You're in IM1 right now. We're going to make sure to find a way to get to that same base, okay? Okay, let's go ahead and get started. Exponential equations are equations in which variables, oh my gosh, I cannot talk. Let's try that again. Exponential equations are equations in which variable expressions occur as exponents. So you're seeing, something like this one right here and this one right here. These are exponential equations. Notice that it's not 6x, it's 6 to the whatever, or it's not 3x, it's 3 to the x power, things like that. Okay, so property of equality for exponential equations. They're saying two powers with the same positive base b that's not 1 are equal if and only if their exponents are equal. So what they're stating here is this goes one of both ways. If you have matching bases here with 2's raised to these powers here, those exponents have to be equal. The only way for this equation to work out is, given that the bottoms are the same, is if the tops here are the same. Right? That's you've seen this in other instances, but for exponential equations, that's also true. And it's true the other way as well, which we won't work off this one as much, but they're just stating something that's true. If you have x equals 5, well, you can raise them with that same 2 base, and you can raise those as exponents. Why would you need to do that here? You say that for IM3, probably a little more so. I'll have to think about a reason why you might want to do that here. But that's true for any base b that's positive and not 1. We've talked a lot about why b is a positive number other than 1 that we use here. So they can use it for any b algebraically, like so. So let's look at some examples. 3 to the x plus 1 equals 3 to the 5th power. As long as the bases match, which they do, you can then ground those exponents. You look introspectively at the exponent sets, that this exponent has to equal this exponent for the left side to equal the right side. You might say, where did the 3's go? Did we divide by 3? No, you didn't divide by 3. You would have used logarithms to get rid of them, which you're not doing. Basically, guys, get rid of them. Introspectively, just look at the exponents. It's kind of like what I said for absolute value equations, right? We look inside the absolute value and we talk about for what conditions would make that part true. And that's what we're doing. We're now looking at the exponents and we look to solve after that. They subtract 1 from both sides. They get x equals 4. That's the value for which this would work. Double check. 4 plus 1 is 5. 3 to the 5th equals 3 to the 5th. It only makes sense that that's the only value for x that'll work. Now, in these other examples right here, if you might notice, this says 6 equals 6 to the 2x minus 3 power. Again, we don't divide both sides by 6, nothing like that, but we do look for matching bases, and hey, these bases match. This is 6 to some power and 6 to some power. Now, I don't see what 6 being raised to here, and I think it's important that you note that is 6 to the 1st power. 6 to the 1st power is 6, not 6 to the 0, and you don't leave nothing there. It is 6 to the 1st. So if these bases match, you can make that 1 occur here. Set them equal, add 3, and divide both sides by 2. You get x equals 2. In this third one, some more of the same. Again, Matching bases, you set the exponents equal and you solve algebraically as you know how to. Get x's on one side of the equation, this time x equals 3. So with the bases matching, it gets pretty straightforward, and I'm sure that's what our first problem set's going to look like. Just basically write the original problem, set the exponents equal, and solve. The next portion, though, I believe, yes, right here is we have to get some bases to be alike. We have to match them. We have to make them the same, but they might start not alike. And maybe there's a way that we can get there. So in this first one, rewrite each side of the equation using the same base. It says 5 to the x equals 125. Our goal here and your goal as the student is to determine how you can rewrite one of the numbers as the other to match the same base. As in, this is 5 to some power. Can I rewrite 125 as 5 to some power? The answer is yes, that's what I would probably go for. And it's not always the case, but, you know, rewrite the larger number like that. You know, that's going to be the way to generally go for you guys. So 125 is 5 to the third power. Just as a reminder, exponents means the number of times that you multiply that number to itself. 5 times 5 times 5. You know, 5 times 5 is 25, times 5 is 125. So it's not like it's 5 times 25, it's not 5 to the 25th power, right? We're not doing 5 times 25, but 5 cubed there. And there's our rewrite. Now that the bases match, we can do exactly what we did before using that property. Therefore, x equals 3. Boom, it's like that. Now, there are some other properties involved. This one called power of a power property. I don't know if I'll always remember the name. Sometimes I say exactly that. I say you raise a power to a power. But it's not technically raising the power to a power. What's happening here is it shows if you have something that's raised to a power already, and that quantity is raised to a power, that's left with the exponents here multiplying with each other. I'm not going to get deep into why that is at the moment, unless we have to get deeper into it for whatever reason, but that's what's going to happen here. Now, why might we need that? On part B, we have 4 to the x equals 2 to the x minus 3 power. I want to rewrite them using the same base. 4 can be rewritten as 2 squared. If I can get them to both match as 2's, then I'll be on my way. But this 4 is the base, and 2 squared is still that base. So I'm going to wrap that around parentheses to state that this thing is still being raised to the x power, and right now that 2 is not yet by itself, right? 2 squared is raised to the x power. I want to make 2 raised to a power. So what do I do now? I exercise this very property right here. These two exponents will multiply. 2 times x literally gives you 2x, and boom, now the parentheses are gone. This can be rewritten as 2 to the 2x. And you can imagine where in some situations you might have to do a little bit more with this, such as distribute a product. In fact, in part C, they're going to do exactly that. So I'll save more for talking about that then. Anyway, you match the bases. Now you can set the exponents equal to each other. 2x, boom. X minus 3, boom. Solve for x by subtracting x from both sides. I'm not doing any double checks right. They are, but I'm not doing any double checks for you personally right here. 9 to the x plus 2 equals 27 to the x power. Okay, this one's a little bit trickier. You know, I said take the bigger number and ask if you can raise that to a power given the other base, like this 9. Well, I can't raise 9 to an integer power to get 27. 9 to the first power is 9. 9 squared is 81. 27 sits somewhere in between that. And there's a fraction version of the number. We're not going to run into that one. But what we want to do instead is rewrite both of their bases. 9 and 27 are both powers of 3. 9 is 3 squared. You can see they rewrote that right here. And 27 is 3 cubed. Now, this is where the problems get a little more challenging, right? They ask you to do a little bit more. For one, it's finding that base that it matches with, and now it's using these other properties. So now that we rewrote those things, we use this power of a power property for both sides. 3 times x is 3x, yes, but on this side, 2 multiplies with x plus 2, the entire thing. There aren't parentheses around it right now, but that idea is happening, right? X plus 2 is the entire exponent. 2 multiplies with the entire exponent. That's why here you see 2x plus 4. But what we ultimately did was got to a scenario where now our bases match. You get like bases. You can now set the exponents equal to each other. So 2x plus 4 equals 3x. Subtract 2x from both sides. You get x equals 4. Here's our good old double check on this thing. You get the left side equaling the right side. Clearly something you can use with the calculator to actually double check with. But they're giving you that good heads up that there it is. So yeah, we're not guessing and checking, right? It's not trial and error. We are actually doing something algebraically to solve them. Now, here's some tricky ones when b is a value between 0 and 1. They mean the base value. You might recall that negative exponents give you fractions. So that's something to be very wary of in these situations. Let's see which way that they want to go about this one. They have 1/2 to the x power equals 4. Now, they made the ultimate decision, and I'd probably agree with them, given what you know and don't know, that they want to match the bases as 2. We know that 2 squared is 4, and this 1/2 clearly is influenced by a 2 somewhere right here. What you have to recognize as fractions are negative exponent values. So 1/2 is also 2 to the negative first power, right? We have a property that can be rewritten like this: x to the m, x to the negative m equals 1 over x to the m. So 2 to the negative first power equals 1 over 2 to the positive first power. But we're actually going this way. For this problem, we're actually going this way and saying, hey, let's turn 1/2 into the 2 to the negative first power. And then use this property again, multiply those two guys. Negative 1 times x is that. Now we match the bases. So, more of the same, set the exponents equal and solve. So a lot of these coming into play. Obviously, I'll have a lot more to do with you in the problem set. There is a part B as well. It says 4 to the x plus 1 equals 1 over 64. Well, 64 itself is a power of 4. It's 4 cubed. So they do one more step in between, one that I like to show you here before we get to that next one. How do we go from 1 over 4 cubed into getting that 4 up top? You turn the exponent negative. So 4 to the negative third is 1 over 64. There's the rewrite. There is that match of base. So they're both bases of 4. This one didn't have to change while we now set the exponents equal and solve. By the way, if you want more practice with these, I'm sure this textbook thing's going to give you plenty, but I did make a video last year, earlier in this year when I'm making the recording, for my students just to get an updated video of something. So if you want more extra practice, I'll put that in the link at the bottom of the description section if you'd like. All right, solving by graphing. Let's see what they do with this. Looks like they say graphing calculator, so probably not as much for us to draw, but we'll see. Sometimes it's difficult or impossible to rewrite each side of an exponential equation using the same base. You can solve these by graphing each side and finding the points of intersection. You can also solve using something called logarithms, which still uses the calculator, and save that for 2 years in IM3. Exponential equations can have no solution, true, one solution, or more than one solution, depending on the number of points of intersection. Yeah, if we see the graphs, we might see different ways that they will intersect. And if I do recall, guys, we have used the intersection feature on the graphing calculator together. Yes, I sometimes forget what I've done for certain classes. I believe for IM1, I've been doing that with you guys. And listen, you might not be assigned to these kinds of problems if you're not using a graphing calculator, in which case, move forward. By the way, did they ever say solve using real-life application? I don't know if we're doing word problems with this one, at least not in a big bad way. All right, use a graphing calculator to solve 2.4 to the x minus 1 equals 5.76. I would actually know how to do that one without a graphing calculator because I know what the decimals are. And 3 to the x plus 2 equals x plus 1. That one's a little trickier. Because we have an x in the exponent and one that's not. That's generally not something that we play with very often together. Just so you guys know, 5.76 is actually 2.4 squared because 576 is 24 squared. So there's probably something that has to do with that we could do by hand. I'll show you that one after. Anyway, we did this together. It's kind of nice that we saw this before in chapter 5. What chapter are we in? 6? This might have been chapter 5. Yeah, systems, where we solved by graphing by writing a system of equations, set y equals left, y equals right, and then go to the calculator, graph them, and find out where they intersect. So you see y equals 2.4 to the x minus 1 looks like this. By the way, we've graphed exponential functions. You might know what that means to have this graph look like this. And then y equals 5.76 is literally just a constant line here. And where do they intersect? So when you use the intersect feature on the graphing calculator, obviously the y value is 5.76. It makes sense there's no change. And the x value is 3. Aha! I don't have to do this other version. They did that right here. 2.4 squared is 5.76. So you can rewrite that as 2.4 squared, set the exponents equal, and add 3 to add 1 to both sides to get x equals 3. Keep in mind the solution is just x equals 3 here, just like it is right there. You're not using the 5.76. It's not a true system. We only set up a system to solve. And there you have it. There's another one right here. Y equals x plus 1, you can see is that blue line, that linear one, and here's 3 to the x plus 2 power. You can see that they don't ever intersect. This one actually just has no solution. Now it's possible you can have ones, they said that they have like 2 solutions. What if the line went like this? Well, now it intersects here and here. Other than that, guys, this one has a no solution instance. And yeah, get ready for anything. I don't know which problems are specifically going to come up. We have 58 of them to do. So yeah, get ready for anything. All right, guys, that is it for the lecture portion. Let's now go into the vocabulary and core concept check before we hit the rest. Number 1 on writing, describe how to solve an exponential equation with unlike bases. Basic thing is get the bases to match. I say matching bases. I don't know if that's a good phrase or not, but get the bases the same. And then solve as you normally would. So there's a lot that's written under the hood with that. Sometimes you have to rewrite both of them with bases. Sometimes you have to do that extra power of a power property. Sometimes you have to work with negative you have to work with fractions and use negative exponents. So there are a lot of different things that will be involved. And there's another one that we didn't run into the lecture portion. I'm hoping we do run into, and I can call out when we do, that we haven't yet seen. Number 2, which equation does not belong with the other 3? Explain your reasoning. As I scan through them, I'm looking at this one being different right here. I'm going to call that one B, whereas these are A. The A's are exponential equations. They have x's in the exponent. This one has exponents, but they aren't variables. They are constants. This is a linear equation. This 4 squared is 16, 3 to the 4th is 81. But hey, x equals 65, whatever. That's not an exponential equation. The others are. And the others you'd have to do more with that you've already seen. And yeah, guys, I think this is going to be more of a drill and kill one. It might actually go pretty quickly, which would be kind of sweet. Let's go ahead and take a look at what's in store for us. Numbers 3 through 58. Get ready. Here we go. Numbers 3 through 12, solve the equation, check your solution. If you scan through this list, oh, that's not true. I take it back. I was going to say, if you scan through this list, you'll see all bases match. Actually, the first 4 have bases matching. After that, we're going to have to match bases for ourselves. So we have 4 to the 5x power equals 4 to the 10th power. And if you followed me on the lecture portion straight up, as long as the bases are the same, y'all, you can set the exponents equal to each other, just like that. Divide both sides by 5, you get x equals 2. It does say check your solution. If I do 5 times 2, I get 10. 4 to the 10th equals 4 to the 10th. That one checks out. It might be a time, guys, I'm not going to be checking my solution each time. But here's the thing. If you can get those parts, if the bases match, I'm just trying to get the exponents to match after that, right? So on number 4, I just need x minus 4 to equal 8. I need to find the x that makes the left side equal the right side. So when I add 4 to both sides, I get 12, right? That's what's going to work. Even if I don't know what 7 to the 8th power is, I know that this side will be 7 to the 8th power because it's going to be 7 to the 12 minus 4 power. 12 minus 4 is 8. And I don't know what 7 to the 8th is. I can use the calculator. It's going to be a massive number. But the point is 7 to the 8th indeed equals 7 to the 8th. So that's my double check, at least for these. Number 5. Matching bases once again, only now this time you have a variable on both sides of the equation. No matter, nothing that we haven't done since, I think, section 1.3. So 3 to the 9x equals 3 to the 7x plus 8 power. We can set 9x equals 7x plus 8 because of them matching bases. And I stated this, by the way, subtract 7x and divide both sides by 2. I stated this in the lecture portion. Where did the 3's go? Well, they didn't divide. Right? I didn't divide by 3. That's not how this thing works. It's not the same thing as multiplication. For now, we can just say we're ignoring them. Well, once we get those to be the same, then we are comparing things equally. The only way for the left side to equal the right side with matching bases is if the exponents are equal. Hey, these are 2's. Great. If these can be the same, if I can find the x that makes these the same, that's what's going to work. So, what value would make these x's the same? That's where we can use algebra, subtract x from both sides, and divide both sides by 3. You get x equals 3. So, yeah, 4 times 3 is 12. 3 plus 9 is 12. 2 to the 12th equals 2 to the 12th. And 2 to the 12th, I believe, is 4,096. So 4,096 equals 4,096. Okay, it's at this stage afterward that we don't have matching bases. And I wouldn't expect many more matching bases at this point. You got some little warm-up questions? All right, now let's dig into this. We get 2 to the x power equals 64. X doesn't equal 64. And this is going to be one of those problems here where you sit and go, even if you knew what 2 to what power 64, which I guess is kind of the goal. You want to say, because literally that's what they're asking, 2 to what power 64. The value is 6, right? So some people will go straight into x equals 6. I would kind of say not so fast, because there are so many other problems where matching bases is going to be so important that we might as well practice it here as well. So instead, rewrite 64 as 2 to the 6th power to get to that same goal that we had here. Hey, get the matching bases before you set the exponents equal. And in this case, setting the exponents equal was the solution as well. right? That stage, we're there. So 64 is 2 to the 6th power. And again, this is one of those things where you might need to know that information, or you might have to test it until it works, or I'll give my students most times something called a power table, which basically has things already written out for the whole set. Or you can use the calculator, right? Do 2 to the 5th power, 2 to the 7th power, 2 to the 6th, it works. All right, number 8. 3 to the x equals 243. And that's literally the same thing as this last problem, asking 2 to what power is, or 3 to what power is 243? But let's do it that other way. Let's imagine 243 is 3 to some power. And then, now that the bases match, we'll go. So 3 to the 3rd was 27, 3 to the 4th is 81, 3 to the 5th is 243. And because it's these, I'm not going to call them basic problems, but it's a problem they assume no calculator, then you can bet it's going to be on an integer value. Even if it's negative, you can assume it's going to be an integer value we're hitting. Number 9. 7 to the x minus 5 equals 49 to the x. Okay, first things first I want to state, because I've done this so many times that I can't count how many times I've seen this. Do not ignore this x. Do not ignore this x. Okay? Did you ignore it? Did you forget it? Okay, no. Okay, you know 49 is 7 squared, so if I can rewrite these with the same base that way, this is where we would need to do extra work, because this isn't just 49, it's 49 to the x power, right? So I can match bases by getting this one to be 7 to a power, right? 7 squared. And then I set the exponents. Wait a minute, I almost forgot that x. That was intentional, right? Don't forget the x. Now, do you just plop the x here? In this problem, you technically could, but let's first, in some problems, you also can't. So let's just make sure 49 is rewritten as 7 squared. 49 was to the x power. Now 7 squared is to the x power. This is where you can now use that property where, yes, these two do multiply, and 2 times x is 2x. So now it looks like 7 to the x minus 5 equals 7 to the 2x power. And this is where your bases are truly now matching. They are the same, out of parentheses, all that kind of stuff. 7 to this equals 7 to that. And that's where you can set them equal and solve. If I subtract x from both sides, I get a 1x, and negative 5 is on that side. So x equals negative 5. Okay, number 10 is a lot like number 9. So maybe we can move on forward with that. Just don't forget the x that's there. It might be even to your benefit to do this. We look like we're going to be rewriting this 216 as some power. Do it straight to that right now. Don't forget it, and understand what you want to do with it. Now, is 216 6 to some power? It actually is. It's 6 cubed. So I can rewrite that as 6 to, and then you think about it, some power. Oh, it's a 3. And then boom, the x was never forgotten or dropped along the way. These exponents will multiply to each other. That's the property at hand that we're playing with. 6 is our matching basis. Set the exponents equal and solve. We will subtract 1x from both sides, and we'll divide both sides by 2. We get x equals 5. Now, I haven't double checked in a long time, so let's do a double check on this one, especially when these are no longer matching bases. I probably should have done it for the previous problem, but I didn't. So if I do a double check here, I can substitute 5. 216 to the 5th equals 6 to the 5 plus 10. 5 plus 10 is 15. Now, this isn't as obvious as to whether it's true or not. If you ask me, I wouldn't know off the top of my head whether or not this was true. So let's go ahead and give that one a shot, and there'll be big numbers. Let's see, 216 to the 5th power. Big. Listen, it's so big that it's not even worth stating what it is. But let's do 6 to the 15th and see that we get the same thing. Oh my gosh, we do. So at least it's the right value there. Okay, this is going to be one of those, like, look at me, I am the double checker now, as far as, like, I'm not going to go back to answer them, really. But that's a good format of double checking and seeing what you do double check with, the original problem, and to show that it actually worked out. Okay, number 11, we have 64 to the 2x plus 4 power equals 16 to the 5x power. This one's one of those trickier ones. It did pop up in the lecture portion. Now, in this problem, I cannot raise 16 to a power to get 64, at least not an integer power. So we actually have to look for a smaller base for both of these values. You might think 8. Hey, 64 is 8 squared. 16 is 8 times 2. Well, that's not an exponent, right? That doesn't matter. So 8 is not a common base. I'm trying to think of the phrase I normally use for this. Common base, something like that, matching base. 4 actually works. 4 squared is 16 and 4 cubed is 64. Now, let's say you didn't know that. 2 also works. 2 to the 4th is 16 and 2 to the 6th is 64. I'm actually going to do, and I'm not going to do this for other problems generally. I'm going to do this 2 different ways. I'll do it with 4, which I recommend, and I'll also do it with 2. Now, 64 being 4 cubed, you want to rewrite like this to begin with before you move on forward with it. 16 is 4 squared. Oh my goodness, what did I just do? I don't want to undo at the risk of undoing a whole lot more. So 4 squared to the 5x power. This is where exponents multiply, but you have to be careful on this guy right here. 3 distributes to the 2x and the 4. 3 times 2x, remember there's still a 4 right here. 3 times 2x is 6x. 3 times 4 is 12. And 2 times 5x is 10x. So you have this here. Now the bases match, and you can set the exponents equal and solve. 6x plus 12 equals 10x. You can subtract 6x from both sides and divide both sides by 4. You get x equals 3. Now, that was with 4 as the base to match with. Let's do it with 2. The main reason I don't recommend 2 is because your numbers in your exponents get bigger. They have to, because 64 is 2 to a bigger number than 3. 64 is 2 to the 6th power. So now you're going to have to multiply 6 with 2x plus 4. And 16 is 2 to the 4th power, which means you have to multiply 4 with 5x. So it gets bigger. But it shouldn't not work, right? It should still work. 6 distributes into these two. You get 12x plus 24. 4 multiplies with this one. You get 20x. Oh, 2 to the 20x, I should say. Now that the bases are matching, set the exponents equal. 12x plus 24 equals 20x. Subtract 12x from both sides. And divide both sides by 8, you get x equals 3. So same answer regardless. I'm going to treat that one as my double check, just the fact I got the same answer with 2 different sets of things. And it still worked out either way. All right, let's go to number 12. 27 to the x power equals 9 to the x minus 2 power. This is like number 11 in that there is neither of these bases represent our matching base. We're going to have to find a smaller base with it. I don't recall if the textbook used these specific. I think it's 27 and 9. It's the same thing though. 3 is a matching base for 27 and 9. 27 can be 3 cubed, and 9 can be 3 squared. So 3 cubed to the x, and 3 squared to the x minus 2. 3 times x goes here. 2 distributes into these. 2x minus 4. So 3x equals 2x minus 4. And try not to skip any steps. I get where there are steps to be skipped. There are some people who could have gone straight from here to here. And some people that could have gone straight from here to here. I'm honestly better off, if you did skip a step, I'm honestly better off in you doing blue, skipping this green part here, given that you know you're going to distribute that, rather than do some of the math within here to get to that other step there. I don't know why. That's just, that's just my inkling. That's my feeling with it. But I'm going to try and do as many of these steps as I can. Maybe I don't have to explain as much anymore that we did those. There you go. All right, numbers 13 through 18 are where we deal with those fractions. Fractions probably to us mean negative exponents of some sort. In 13 through 18, solve the equation, check your solution. So the first one, 1/5 to the x power equals 125. And I've stated this before. Note how they are wrapping the fraction around parentheses when raised to an exponent. That's actually a required bit so that both parts are raised to the exponent. Anyway, it sure looks like 5 would come in handy as a matching base here if possible. And we've seen this a couple times, even in the lecture portion. 1/5 is also 5 to the negative first power. So that's my rewrite of this particular one. 125 is 5 cubed. I think we saw that in the lecture portion. -1 times x is -1x, or just negative x. And there we have our matching bases. So if negative x equals positive 3, then positive x equals -3. That is our solution. You can double check it. I'll go ahead and try that one in the calculator. I won't do very many of these ones, but if I do 1/5, which is also 0.2, but 1/5 to the negative third power, I should actually get 125. There it is. So here's my double check on that one. Number 14. 1/4 to the x equals 256. A lot like number 13 in that, hey, you know, maybe 4 works out. Can I raise 4 to a power to get 256 is the question. The answer is yes. This is 4 to the negative first power, which is raised to dat x. And then 4 squared, 4 to the fourth. 4 to the fourth is 256. So now we match bases now that we have a negative x there. Same thing as before. If negative x is positive 4, then positive x is negative 4. Whether you say divide both sides by -1 or something like that, switch the signs, that's what we get. I won't double check it, but there you have it. Number 15 and likely 16 are kind of the opposite version of what we had before, where this time the fraction is not raised to the exponent, but you still need to do a rewrite of sorts. I'd actually argue this one's easier because you don't have to do a distribution or a multiplication of exponents here. 2 is our base here. If I could make this as 2 here, that'd be awesome. So let's just first turn this into what it is. It's 2 to the 7th power, which is great. Now, are the bases matching? You're on the right track, but this isn't yet 2 to the power equals 2 to the power. This is 1 over 2 to the power. This is where we can get this into 2 to the negative 7th power like that. You're likely going to see me, I think the next problem has the same kind of thing. You're likely going to see me skip this step next time and go straight from there to there. So negative exponents work exactly in that format. That's what we did with it. We now have matching bases. We can set the exponents equal. It's just a -7, right? Yeah, I think so. I'll subtract 3 from both sides and divide both sides by 5. You get x equals -2. Number 16 feels very similar. I believe we even did 3 to a power to get 243, so let's talk about that here. That's 3 to the 5th power. So here I have 1 over 243. If 243 is 3 to the 5th, then 1 over 243 is 3 to the negative 5th power. So 3 to the 4x minus 9 equals 3 to the negative 5th power. And now we set the exponents equal to solve. There I added 9 to both sides. Now I'm dividing both sides by 4. The x equals 1. That's it. That's kind of an easier double check. 4 times 1 minus 9 is -5. 3 to the negative 5th. Hey, that's 243. Or 1 over 243. Well, this looks confuzzling. Let's have fun with this one. Number 17. Yeah, they expand pretty fast on these ones. And I did state at some point that I will probably attach another worksheet with video stuff. Like a video, excuse me, that has a link to another worksheet that I had with, I think it was 24 problems. So eventually we might get into problems like these ones, but it might progress a little more slowly. Again, if you want to check out more problems, you can. I teach it very slowly again. 36 can't raise to a power to make 216, you know, this kind of thing. But we just saw 6 before that works. So let's match this as 6 to some powers and just go off of that. So 36 is 6 squared. So let's start it off like that. And 216, now if you understand how this stuff works, 1 over 216 is 6 to the negative 3rd. So negative exponent, ahoy me hoy, we work that way. And we have to do a distribution. We got to do 2 times negative 3x plus 3, so that's negative 6x plus 6. And here, negative 3 times x plus 1, that's negative 3x minus 3. So the bases match. We now set the exponents equal, and we go on our solving ways. I will add, let's see, I'll add 6x to both sides, and I'll add 3 to both sides, and I'll divide both sides by 3, and you get x equals 3. I don't know if I want to double check that. I think it's fine. Number 18. We have 1 over 27 to the 4 minus x equals 9 to the 2x minus 1. Again, we've seen 9 and 27 together as matching with 3. You know, 3 can be their base here. 27 being 3 cubed means 1 over 27 is 3 to the negative cubed as to the negative 3rd power. And 9 is 3 squared. So now let's distribute these. The negative 3 distributing, I'm going to be that guy. I'm going to place the x term first here. Negative 3 times negative x is positive 3x. So this becomes 3x minus 12. It's easier for me to look at that way. And 2 times 2x is 4x. 2 times negative 1 is negative 2. Bases match, set the exponents equal. You've heard it 15 times before. Subtract 3x from both sides, you get x. Add 2 to both sides, you get negative 10. Okay. Okay. I'm trying to see where this goes from here, but yeah. I expected a lot more. I expected that to spread itself out a lot more through the problems, but only being about a third of the way through or whatever it is. What are other kinds of questions we have? Because that seemed like most of the lecture portion besides graphing calculator. All right, in exercise 19 and 20, describe and correct the error in solving the exponential equation. The first one I'm seeing is they never match their bases. They set the exponents equal without doing that. Now, we're going to have to correct it. We're going to have to do it for ourselves, but they set the exponents equal. They have to match bases first, right? You can't set these other parts equal if the parts on the bottom weren't equal to begin with. So let's check it out. So 5 to the 3x plus 2 equals 25 to the x minus 8. Let's rewrite 25 as 5 squared. I think we now have a handle of this a little bit after this set of problems. And distribute the 2 into those two terms. Now the bases will match, in which case you can do this properly. So this is 2x minus 16. So this 3x plus 2 ain't equal to x minus 8, but 2x minus 16. From there, you can go ahead and solve that thing. 2x subtracted, 2 subtracted here, you get negative 18. Am I right? I guess so. I hope so. They didn't double check either, right? That was probably part of their problem too. Number 20. I see rewrites with matching bases and such. I'm going to talk about the error. It's right here. But let's make sure everything else works out. Distribution of, multiplication of, set things equal, subtract 5 to every 10. Okay, the problem here lies with this portion. They rewrote 1/8 as 2 to the third power. And 2 to the third power is indeed 8. But because it was a fraction base, we need to raise it to a negative exponent. So everything else is looking good. Obviously, it's going to change the rest of the problem. Actually, maybe not fully, but just a little bit. A fraction base was not rewritten with a negative exponent. Point blank, that's the idea. Now, they didn't write the in-between step where they could have written 1 over 2 cubed, right? We could have begun with that. So maybe they can do 1 over 2 cubed, but it's still not a matching base until you kind of do more with that. In which case, this is where you would say 2 to the negative third. Oh, I forgot to rewrite this one. I'm sorry. 2 to the 5th to the x plus 8. Everything they did on the right side was fine. They distributed properly, everything like that. And this is 2 to the negative 15x instead of positive 15x. So it's sure going to look the same as it did before until their final solving actions right from here. Turn this negative. Now, I'd like to add 15x to both sides. Let's call it 20x, subtract 40 over here. Way different answer. Divide by 20, you get x equals negative 2. Okay, negative 2 instead of 4. We're good. All right, numbers 21 and 24. It looks like this is where we start to do some solve by graphing stuff, but here we're going to match. It says match the equation with the graph that can be used to solve it, then solve the equation. So for these, this is kind of where we would look to do the whole set y equal to this and y equal to that kind of thing. So I'll write that for this problem. I think the other ones I'll just kind of state that out loud. We're looking for y equals 2 to the x and y equals 4. It's not going to be a because this is an exponential decay problem. 2 to the x would be an exponential growth problem. I need to find one where y equals 4. Oh, looks like they all have y equals 4. So these are all constants. Y equals 4, 4, 4, 4. So which one's y equals 2 to the x is basically the question here. I think it's this one right here. This has a y-intercept of 1. You have to remember that y equals 2 to the x means 1 times 2 to the x like that. The y-intercept of 1 and a growth of 2 where we're doubling and doubling like that. So 2 to what power is 4 is 2, and that makes sense here that we get x equals 2. So this answer will be C. So the graph that we're matching with is C. The answer is x equals 2. Remember, we only use the x. That gets us that same y, but not the y itself. Did we know that 2 to the x was equals 4 gave us x equals 2? Yeah, I'm sure we did. But we're using the graph thing to make sense of and match how that stuff works. We just did number 21. Let's do number 22. Number 22, now let's kind of get rid of some of what I was drawing here. Let's get rid of C. And number 22 says for to the 2x minus 5 power equals 4. Now, keep in mind, all of these do have equals 4 on the right side. So that blue line's the same no matter what we do. It's also not a, because this also has, and I mean, you can see all these numbers right here, and you say none of these are fractions. I get it, but we're going to talk about which one kind of does. But that 4, for all intents and purposes, that 4 is more than 1. So you're going to see exponential growth on this one. Now, the y-intercept to you would have still been 1, but notice that this has a shift. So this one's a little bit different. This one's a little trickier to talk about. I might want to just dive into this part a little bit more, get the y equals on the way. I want to talk about this in a best way for you, because you guys have seen that whole y equals a times b to the x minus h plus k, but you haven't seen one with a number in front of the x as well. If there was some sort of, I don't know, a q times x minus h plus k, whatever it is, and that changes things. This isn't even a horizontal shift 5 units to the right. You'd have to say, for what value here do you get 0? And that answer is 2.5. So we're actually going to shift this thing 2.5 units to the right before we multiply by 4 and by 4. That's actually going to give us a graph of D. So this is going to be a little bit weird. But look, if I go 2.5 units to the right, look where it hits a y, not a y-intercept of 1, but look where it hits y equals 1, right there. Boom. And then when we go over a certain amount here, then that's where you get that 4 as well. And that's at x equals 3. So this one's a little bit trickier to talk about, but the minus here can make you think that there's a right shift, and so that's where that's going to happen here. But this is D, and it'll be x equals 3. You can double check by substituting 3 into here. 2 times 3 is 6, 6 minus 5 is 1, 4 to the first power is 4. That does work. A little trickier of a problem, and it's harder for me to kind of talk about with it because we haven't seen that exact kind of thing before. All right, number 23 says 2 to the x plus 2 power equals 4. Now we're going to look for the y equals 2 to the x plus 2 graph. This is one we have seen more of, and this x plus 2 means we are going to shift 2 to the left to get the graph that we want. And that's going to look like graph B. When you notice that we would have had a y-intercept here at 1, and now when we shift this thing to the left, that 1 actually appears right here. And then you double as x increases by 1. X increases by 1, you double, x increases by 1, you double. And substituting 0 in for x is what's going to give you 4 out. 2 to the 0 plus 2 is 2 squared, which is 4. This is graph B, and x equals 0 is the solution to this one. So number 24 must be A. So what makes number 24 give you exponential decay, despite the fact that you have a 2 as a base value here? Well, like I stated before, this isn't truly just a 2 because this isn't just an x right here. So for this equation, y equals 2 to the negative x minus 2 power, I can, I haven't said the word factor very much, and I can't really introduce it as well as I'd like to, but this is 2 to the negative first times x plus 2. If you think about the fact I could distribute a negative 1 into both of these to make these negatives, you can make this a 2 to the negative first. And how do negative exponents work? They turn into fractions. So this would be 1/2 to the x plus 2 power. Now, does graph A resemble y equals 1/2 to the x plus 2 power? Well, it probably does. 1 would be your y-intercept, except we're shifted 2 units to the left. So instead of being 1 right here, we're shifted 2 units to the left, and boom, we're right there. 1/2 being exponential decay means every time x increases by 1, we'll take half of what we had before. Over 1 and half of what you had before. Over 1, half of what you had before, which means when I go left 1, we multiply by 2, and left 1, we multiply by 2, which means x equals negative 4 is where you're going to get 4 out for this thing. So this is graph A. This is x equals negative 4 as an answer. We're good to go. So trickier problem, a lot more to work with. We didn't actually graph, but we use the understanding of graphs to make matches. All right, let's go to 25 to 36. Guys, that is 12 problems. It says use a graphing calculator to solve the equation. It doesn't say double check, so maybe these go fast, maybe these go slow. I'm not sure. All I know is I got to plug them in and go, go, go. So the first set is 0.25 to the x plus 2 equals 16. And remember, that does mean what I'm going to do in the graphing calculator is I'm going to make this a system of equations that's y equals 0.25x to the x plus 2 and y equals 16. Now, that's not to say that we couldn't have done this by hand. 0.25 is 1/4, and 4 can be the base for both 1/4 and 16. It's possible to do. But let's use the graphing calculator and go off of that. Because it was instructed. It was asked of us. Now, in my graphing calculator here, I need to put x plus 2 in parentheses for the exponent. It's not going to put the plus 2 up there if you don't do it that way. Because this is y equals 16, you know you're going to have to get that y value up to at least 16, so I'm going to turn it into 20. You know if you want to find the point of intersection, you have to get up there. Because the y value is going to be 16, but we need to know what the x value is. So where do these intersect on x? Looks like, I think, -4. Use the intersect function, option 5. First curve, second curve, and boom. We're going to get x equals -4. Now, I don't intend on writing very much for myself on these problems. I'm probably not going to write very many of the systems of equations here as well. They just said use the graphing calculator to solve. So like I said, I'll probably just write the problem. I'll do the rest in the calculator, and I'm going to write the answer. They don't even ask you to double check, so I don't see a need to do that. Now, that being said, I did state that the majority of these can probably be solved by hand, meaning something that you might know how to do. For example, 1.9 squared is 3.61. So like there are things there that you can do. But let's go to the graphing calculator for this one as well. The one thing we might have to tool around with, and you just saw me do it for the previous problem, is our window range. So x minus 4 and this one, and this is 3.61. So this one here, I'd like to probably zoom in back to at least 10 here, because we're going to hit 3.61 on y as this curve is drawn somewhere. Okay, there's the curve trickling through, and 3.61 going across here. Let's add x equals something, 5 or 6 or something like that. X equals 6. X equals 6. So on this one here, we'll do x equals 6. So yeah, I don't have much to say on these unless I did the version that I did by hand. I'll tell you which ones I won't mind doing by hand and which ones I would. I would mind doing this one by hand without use of a calculator. I don't even know how I would without use of a calculator. But, 2 and 9 don't share a common base, right? So it's this kind of one where the graphing calculator is not only going to be very helpful, but this answer is also probably not an integer. So 1/2 to the 7x plus 1 power equals -9. So we'll do y equals 1, y equals the other like that. Now the 1/2 needs to be in parentheses, as it actually was for the problem, right? So 1/2 to the, and then of course 7x plus 1 in parentheses here. So if anything, gets practice some order of operations. All right, -9 should fit down at the bottom. Let's see. Now, some of these won't intersect. Actually, this one won't intersect. So maybe I could have done this by hand just by knowing that this one will stay above the x-axis the entire time, and then the other wouldn't at all. Maybe that's why they presented it this way. This is no solution. This is no solution because I should have noticed that immediately. There's nothing I can raise this to a power to get 0 or negative, so that never would have worked. Now, number 28 could work possibly with this, meaning they will have a solution somewhere, and I could match bases this time. So maybe that's why they gave us one that couldn't match bases, because it wasn't going to have a solution anyway. This one you could match bases with 3. I don't know why they don't have us do it without a calculator on those ones. I don't know. 1/3 to the x plus 3, and then +9. Okay. So we're going to see up here, probably intersect around -4, it looks like, because that goes across. Let's see this one. -5. X equals -5. Good thing we're not here to eyeball it. Okay, number 29. 29 is among those that I would not do by hand, personally. So either these do intersect, they don't, I have no idea. Oh, I imagine these ones intersect for sure, for sure. Oh, actually, wait. Oh, I think these intersect. I think these intersect at x equals 0. I state that for reasons. You'll see the graph. We'll see if they intersect somewhere else. But I want to see if these intersect at x equals 0. I know they will. I don't know if they'll intersect somewhere else, though. So 2 to the x plus 3. So this curve, remember this is a curve with exponential growth, but it's shifted 3 to the left. It's going to hit the y-axis at x equals 8. That's why I brought up what I stated. And then this one has a y-intercept of 8. We know this just because of 3x plus 8, y equals mx plus b. So let's see. It's going to curve up like this. The other one's going to draw through like this. Oh, it intersects twice. Okay, I didn't know that. So it intersects twice. So the first place that I do know it intersects is first curve, second curve. Up here will be at x equals 0 and y equals 8. So that's one of the solutions. So x equals 0 is one thing I'm writing. I did not know whether it would intersect a second time, and this is where the graphing calculator is very helpful for us. So let's find the other one. Intersect, first curve, second curve, but when we guess, let's get it closer to this other point of intersection over here. That's x equals -2. So x equals 0, x equals -2, our 2 there. Number 30. Same kind of problem. I'm not going to really guess where these ones intersect. This is where the graphing calculator comes in full force. Okay, so let's get it. 4 don't forget the parentheses here. All right, I don't know if they intersect on visible axes. Okay, they do. All right, I want to zoom in on this a little bit. I don't know if you can recognize, guys, but these actually intersect at more than one place. At least it looks like it to me. Let me zoom in here. I think you'll see more spacing. So look at this curve, intersects there and then there. So there are two different spots. I'm guessing it's x equals 1, x equals 2, right? It's kind of what it looks like. They probably gave you good values there, because otherwise if they don't intersect at, yeah, x equals 1, y equals 1. So x equals 1 is one of them. Let me just write that really fast. And then I'm guessing the other one here is x equals 2. We can even go to the table. At x equals 2, looks like they have the same y value of 5. So as long as they have that, that'll work out. So x equals 2 is the other. So notice that x equals 1 and x equals 2, they share the same y value. Outside of that, they do not share the same y value. So it can intersect twice. We've now seen that a couple times. Number 31. We have 4/3 x minus 1 equals 1/3 to the 2x minus 1 power. Yeah, once again, when you have exponents in, when you have variables in the exponent and variables outside of the exponent, not really easy to solve algebraically. So let's bless the graphing calculator for those ones if we're not in IM3 and using logarithms. Now, I don't know if they'll intersect within our window range. I know I'm zoomed in still, so we'll see what this does. To the 2x minus 1. All right, let's just see what it looks like right now to begin with. Okay, just one intersecting point, and we know exponential functions just do that. That might be x equals 1 again. Let's check on the table and see if it is. If it's there, it is. Take a look. You get the same y values here, 0.3 repeating. 1/3, right? When you substitute 1 for x, you get 1/3 for y, apparently. So I'm going to say, now that's x equals 1. Don't worry about the y value of 1/3. That's just the y value that comes out when you substitute 1 for x in both of those. Number 32. Problems get crazier looking, but it's still all up to the calculator to do everything for us, so I don't think that's really too much of a problem. We just got to make sure we still know our order of operations as we go through. Now, this could be rewritten in slope-intercept form. They both divide by 4. They just made it very weird looking. So, problem them, not us. 2 to the negative x plus 1, parentheses around that guy, and then parentheses up above here, 19 minus 5x, 15x, all over 4. As long as you're going to write it the way that they have it written, you have to make sure that you use parentheses when grouping something like that. So let's see if both of these intersect together here. Okay, there's an intersection point right there, but I can imagine, we talked about this comparing linear and exponential. These are going to have to intersect somewhere up here, because this thing's about to curve up and pass it. So I got to zoom out again. Let's go here and see if we find that spot. Okay, just missed it. Let's zoom Y out, about 20. There it is. Okay. First one looks like x equals 1. I'm going to check on the table for that one. Yeah, first one's x equals 1. Let's use the intersect feature for the other one. So the other one, intersect feature, first and second curve, but let's get closer to this point of intersection. So when we guess, it finds it for us. Probably -3. -3. So x equals 1 and x equals -3 are the two answers. Okay, number 33. Once again, bases that probably couldn't match and solve very well algebraically outside of some IM3 logarithm work. I don't think these ones intersect. Okay, so. Because the first one will be above the x-axis, 5 to the x power, and the other one will be below the x-axis. Remember, this is not a -4. This is the opposite of 4 being raised to this power. So this is a negative growth graph. This is a positive. Well, actually, it's negative decay because the x is negative here. But this is positive growth. So one's going to take off like that. The other's going to go like that. But they actually won't ever intersect. This one's going to come from the bottom like that. Boom. Total misses. So no solution for this one. Not even close. No solution. No mistakes. Just no solution. 3 more in this set. Number 34. And this is one, it's possible that these ones don't intersect. I don't know as a for sure. And this is, I don't even know if the graph is going to be very telling of this just because of how close it goes to asymptotes. What I'm looking... Oh, actually, they should intersect at x equals 2. They should intersect at x equals 2. I forgot. I'm forgetful of these things. Okay, I think they're going to intersect at x equals 2. So 7 to the x minus 2. Whoops. And 2 to the... Okay, I want to change my scale back at least to normal here so we can see that inside part. At x equals 2, they should have both a y value of 1. So that's 7 to that power, and 2 to that power is going to come from there and cross through. So you can't really see it as well, but this is 7 to the x and 2 to the x, but they're shifted just over to the right a little bit. So instead of intersecting at x equals 0, they intersect at x equals 2. They both share a y value of 1 here. So x equals 2. Now this one, as far as double check goes, 7 to the 2 minus 2 is 7 to the 0, which is 1. 2 to the 2 minus 2 is 2 to the 0, which is 1. So they both share that value. Number 35. These should intersect. Oh, yeah. These should intersect. I don't know where. Yeah, I do. I think at x equals 3. All right, 3 to the... There's a lot of problems to do with the graphing calculator. I wonder what their angle was with this. There's no x there. Okay. X equals 3. There it is. That's at x equals 3. All right, x equals 3 on that one. Yeah, sorry, I don't have much to say on these problems after we kind of graph them, so I'm just trying to anticipate answers beforehand and get a visual of what that graph would look like. Number 36, I believe, is another one that will have no solution because 1 is once again a positive. This is a positive decay, but it's going to stay above the x-axis the whole time, and this is a negative growth. It'll stay below the x-axis at all times. So I don't think these ones will intersect. We'll probably have a no solution case here. But they said solve by graphing, so we shall write it. 5 to the negative 2x plus 3. You can shift all you want left and right, but if you don't shift up and down, Oh, raised to the... Nope. Raise the... Okay. So positive decay. That shot down fast, too. Negative growth. Yeah, no, not hitting. So no solution. No solution. Okay. There's some graphing ones. We use the graphing calculator. I just didn't draw graphs for them. In exercises 30 to 40, solve the equation by using the property of equality for exponential equations. Well, I think it's just something that we had before. This is just the next step forward on these, and this is a set that I do believe would have existed on this other worksheet that I keep bringing up. You know, what we haven't had to do yet was isolate our exponential term. So this is what we need to do here. No, I will not do 30 times 5 because 5 is raised to this power first, but 30 times something is giving us 150, and we have to figure out how to work that out. So first thing I'm actually going to do, and I won't write this really often if ever after this, is divide both sides by 30. I have to get this guy here by itself so that I can start to work on what it is I want to work on. And 150 over 30 is 5. So now we have this thing by itself, and now it's all about matching bases. Well, the bases match, but this also means 5 to the first power. Don't forget that part. So that means x plus 3 equals 1, therefore x equals negative 2. So that's the set, right? Get this thing by itself so we can do some work on it afterward. Number 38, more of the same. On number 38, we have 12 times, now I kind of want to use parentheses here, times 2 to the x minus 7 equals 24. I like kind of looking at it more that way. If I divide both sides by 12, now it'll say 2 to the x minus 7, no parentheses needed, equals 2. Matching bases, and once again, that is an exponent of 1. So that means x minus 7 equals 1. Therefore, x equals 8. So you can see I now start speeding through these after we've done some problems like it. Yeah, the first step was new, but not from something we haven't done before, if not at least on just number 37. 39 and 40, a lot like what you just saw. So number 39, we have 4 to the, or times 3 to the negative 2x minus 4 power. That's all written in its own set of parentheses. Equals 36, and we divide both sides by 4, and you get 9. Now 9 is 3 squared, so this can get us to match bases here like that, and then we can set these two parts equal. Negative 2x minus 4 is 2. If I add 2x to both sides and subtract 2, I get that, and divide by 2, you get x equals negative 3. Number 40 should probably be looking like 39 a little bit. All right, let's divide by 2 to isolate the exponential term. And you get 64, and 64 is 4 cubed. So now we can set 2x plus 1 equal to 3, subtract 1 from both sides, divide both sides by 2. You get x equals 1. Do the double checks all you want. I'm going to leave them. Okay, we do have some word problems, despite them not doing any examples with them. Modeling with mathematics. You scan a photo into a computer at 4 times its original size. You continue to increase its size repeatedly by 100% using the computer. The new size of the photo y in comparison to its original size after x enlargements on the computer is represented by y equals 2 to the x plus 2 power. How many times must the photo be enlarged on the computer so the new photo is 32 times its original size? So the size of the photo is y in comparison to the original size after x enlargement. So I believe that they're stating set y equal to 32 to solve here. Not to be 32 times larger than 2, but just 32 times larger than the original. So 32 equals 2 to the x plus 2 power. We solve for x, and in solving for x, that's how many enlargements we would have had. So they give us, I guess the reason they're not calling this a true word problem is because they're not making us write the model. So 32 is 2 to the 5th power. And now that the bases match, we set the exponents equal. We get x equals 3. So 3 enlargements would get what we want there. Now, they said you scan a photo that's 4 times its original size. That's accounted for with this x plus 2 part. I know there's probably not a... we might have mentioned this before, but this can also be rewritten as 2 to the x times 2 squared. That when you match bases through a product, you add the exponents like that. That means this is also 4 times 2 to the x power, like that. So that's where the 4 comes from for the initial bit. I don't have to do that for the problem. I'm just, and you could have done it for the problem, but I'm just stating that this is where that 4 comes from, and then that increasing by 100% is where this 2 jumps in after that. All right, number 42 says a bacterial culture quadruples in size every hour. You begin observing the number of bacteria 3 hours after the culture is prepared. So even though it quadruples every hour, you only saw it after a right shift of 3 hours after. Excuse me. The amount of bacteria, Y bacteria, X hours after the culture is prepared is represented by here. When will there be 196,608 bacteria? So we have the original model here, and we will do our solving. We're going to set 196,608 equal to Y. Now, I will use the calculator in dividing both sides by 192. So I'm going to at least write that so you know what I'm calculating. But I'm going to divide these by 192, which isolates my exponent term. This is kind of what we were doing on these numbers up above right here, 37 to 40. So we're going to apply that to this problem here, where I'm going to do 196,608 over 192. And I get 1,024. So 4 to the x minus 3 equals 1,024. And this is where we have to rewrite 1,024 as 4 to a power if we can. And I believe it's 4 to the 6th. No, 4 to the 5th. 4 to the 5th, I think. And that's where we can now set the exponents equal and solve. So x equals 8. So 8, after 8 hours of you observing, because you started, so I wonder if they want to say 8 or 11. Let's see, 3 hours after the culture is prepared. When, after 8 hours of you observing, I think it's just after 8 hours. I don't think you add 3 to it. I think it's just after 8 hours that we stayed there. Okay, numbers 43 to 46, they say solve the equation. They don't give any other instructions, so they say go right into it. I believe they mean algebraically, not with graphing calculators. So let's see how good we are at this stuff now that we've gotten this down a little bit. 3 to 3x plus 6 equals 27 to the x plus 2. Doesn't really look more challenging than the last set of problems we saw in the very first block. We got to match bases, and we can with a 3. Turn 27 into 3 cubed, like so, and distribute the 3 into here. Oh, these are different. You distribute the 3 in here, you get 3x plus 6. 3 to 3x plus 6 equals 3 to 3x plus 6. Well, these are indeed the same equation. Therefore, there are infinitely many solutions. I wonder if I should say that or all real numbers, but there are infinitely many solutions for this one. This is one of those ones where, oh, here, listen, I'll keep going on this. You set the exponents equal, and then you subtract 3x from both sides, and you get 6 equals 6. So it's one of the cases right there where we get to that conclusion. But basically, the left and right are the same equation. So I guess these are special cases. I thought these were supposed to be more challenging problems. I guess not. All right, number 44. So expect all special cases, I guess. 3 to the 4x plus 3 equals 81 to the x. 81 being 3 to the 4th power. Like so. So this is 3 to the 4x plus 3 equals, now you multiply these 3 to the 4x. Now if maybe you don't notice what's happening just yet, but now that the bases match, set the exponents equal, and subtract 4x from both sides, you get 3 equals 0. That's a no solution case, as we've seen in the past. So these graphs never intersect. One is the same growth rate as the other in all instances, but it's shifted a little bit to the left in comparison. Number 45. I wonder how I want to represent this one. But number 45, because I have an easy version for myself, 4 to the x plus 3 equals 2 times 2 to the x plus 1 power. Equals 2 to the 2 times x plus 1 power, excuse me. This is one where, and I kind of did this for another problem where I even had to work one more step into it. Instead of trying to match bases immediately, you might know that 2 squared is 4, and we can actually work this out in that way. Because 2 is a product multiplying into x plus 1, even though it didn't distribute yet, we could rewrite this as 2 squared here to to the x plus 1 power there, and 2 squared is 4. So now we get 4 to the x plus 1, and now we match bases without needing to actually really do anything. We just rewrote what's already there. So now we have x plus 3 equals x plus 1, and subtract x from both sides. We get 3 equals 1, which is one of them no solution cases. And then number 46, 46 might be the same with this. Oh, 5 to the 8th power is not 625. So I wonder how I should best rework this one. But 46 is 5 to the 8 times x minus 1 power equals 625. Oh, to the 2x minus 2 power. Okay, there's some work I could do on here, and I'm trying to think of how I want to work this one best. Let's do... I'll start with this. 625 is 5 to the 4th power. So at the very least, what you'll see here... I'm trying to decide whether I should do distribution or how I should work this one out. How about this? I'll rewrite this one as 5 to the 8th, to the x minus 1, kind of like how I did the other one. 8's multiplying with the x minus 1, so we can rewrite it like that. And here, see, this one will be a little bit trickier. I'm going to have to do a couple things. 4 can distribute into the 2x minus 2, sure. But you can also factor a 2 out of the 2x minus 2 and turn it into 2 times x minus 1. And I'm going my own way about these problems, if that makes sense. Maybe it's not one that you fully understand with it. It's how much you understand factoring from what we've done in the past. But the 4 can multiply with the 2 and turn into 8 here. So we get 5 to the 8th here. And that's to the x minus 1. Now, I can go back and do some more stuff on this. The bottom line is I don't know what 5 to the 8th is, and I don't have to distribute the 8 into them because they're the same. As long as these bases match, I can set x minus 1 equal to x minus 1 and be all good. Set those exponents equal, subtract x's, you get negative 1 equals negative 1. This is infinitely many solutions. So you could do other things. I tried to just avoid calculator usage. Like I could have, I could have done 5 to the 8th power, gotten some number, figure out what I have to do with the 625. I'm going to kind of avoid that if at all possible, and it looks like I did there. Okay, number 47, number sense. Explain how you can use mental math to solve the equation 8 to the x minus 4 equals 1. This was the question. I was going to bring this up before, and I stated they didn't show it up in the lecture portion, and they made it its own special problem. This was the one I was talking about, when you have 1 on this side. Now, if your goal is base matching, I want to rewrite. See, normally you rewrite like the bigger number and something else. But I can't raise 1 to a power to make 8. But I can raise 8 to a power to make 1. I can raise any number to a power to, except for 0. I can raise any number to a power to make 1. I raise it to the 0 power. 8 to the x minus 4 equals 8 to the 0, right? I have to figure out what I plug in here to make this 8 to the 0. So that's what we say. X minus 4 equals 0 and x equals 4. It says explain how I can use mental math. I'm showing you. This is my explanation. 1 is 8 to the 0 power. Anything to the 0 power is 1, provided that that base is not 0, and it won't be. We're not worried about that. Okay, number 48 in problem solving. There are a total of 128 teams at the start of a citywide 3-on-3 basketball tournament. Half the teams are eliminated after each round. Write and solve an exponential equation to determine after which round there are 16 teams left. So this is one where we can maybe start it with like a y. Don't worry about the 16 yet. Start with this situation. Y is the number of teams that are in the tournament. We start with 128. Make that kind of like your initial, your y-intercept. Don't worry about the 3-on-3 aspect. The number of players isn't relevant to the problem. What matters is the growth or decay rate. In this case, you eliminate half of them after each round. X can be the number of rounds. If I say round 0, there are still 128 teams. After round 1, boom, half of it, 64, etc., etc. So we can write our equation like this. Now we set y equal to 16. 16 equals 128 times 1/2 to the x power. Now you could do guess and check. You could do it mental. You could take half of 128, etc., over and over until you get the answer. Let's do it more algebraically. Let's do a little more of, divide both sides by 128. I'm going to reduce this fraction of 16 over 128. Now on this side I have 1/2 to the x power, and on this side 16 over 128 is 8, 1/8, like that. So let's do this algebraically and work out the rest from there. So 1/8, it depends on if you want to match bases from here or get them as negative exponents, like make them 2s. Like this is 2 to the negative third power, and 1/2 is 2 to the negative first power. So you can match integer bases if you'd like to. And negative 1 times x is negative x. So we have negative 3 equals negative x, or positive x equals 3. After 3 rounds, you have 16 teams left. Does that work? So after 1 round, you have 64 teams. That's half of 128. After 2 rounds, you have 32 teams. Yeah, after 3 rounds, you have 16 teams. Sweet 16 comes 3 rounds later. 10 questions to go. Number 49. You deposit $500 in an account that earns 6% annual interest compounded yearly. Sounds like something that, or annually, sounds like something we did in section 6.2. Write and solve an exponential equation to determine when the balance of the account will be $561.80. So let's come up with an equation there. Y equals A times its interest. So 1 plus R to the t power, and it's yearly. There's no quarterly compounded or anything like that. So our equation is going to look like this. And I'll write to the t power here, the when. And we're going to set y equal to $561.80. And again, instead of doing guess and check and see when it does work, let's just do it algebraically and come up with that answer. Of course, because it is a decimal, maybe we'd have to use the calculator, graphing calculator at some point here. I get it. Like right now, I kind of want to do that. What's 561? I'm going to do this right here on the calculator. 561.8 divided by 500. And I'm getting exactly 1.1236. Not exactly the most enticing number. I get it. But this is where we are at with our equation. This is one of those things where, hey, what power can I raise this to get it? So I'm actually going to do a little bit of guess and check here. I hope you don't mind that. Normally, I wouldn't do this kind of thing. What if you square it? What if, oh, when you square it, that's the answer. So I didn't know that, but I was going to say, what if you cube it? But I guess it's when you square it. So these are both 1.06, like this 1.06 squared equals 1.06 to the t power. So t is 2. What are they saying? After how long will you have this much money? After 2 years. 2 years. And I forgot if I wrote 3 rounds for this last one. I did not, but after 3 rounds, because they are word problems. 3 rounds here, 2 years there. We get 16 teams and that much money. All right, number 50. How do you see it? The graph shows the annual attendance at 2 events. Each event began in 2004. So we have an event with an increase, event 1, event 2 with some sort of decay, I don't know, attendance. Estimate when the events will have about the same attendance. We're trying to find around what x here. It's about after 3 years from 2004. So year 0 is 2004. So around 2007. 3 years after 2004, right? So around 2007 is going to be my answer. Part B, explain how you can verify your answer in part A. Well, we can substitute 3 into those equations and see what the attendances are. Now, it appears to, did I spell that wrong? Attendances. That's right. Maybe attendances is not a plural word. That's okay. What the attendances are. What attendance is? It's 2 attendances. Isn't that plural? Anyway, so it appears to me that it might be slightly more than 3, but as long as that's the one that gets you close to it. Now, keep in mind, 2007 is 3 years after 2004. I don't substitute 2007 into the values. I substitute 3. But if I do, and I know I hid the equations from you now, but if I do 4,000 times 1.25 cubed, and if I do, so there's that number, that's the attendance, and here I do 12,000 times 0.87 cubed, it's going to be close to the same number. That's the goal, right? So about the same. It's supposed to be a little more after 3 years when they're the same, but that's the verification. You can, of course, also graph these equations and use the intersection feature. That might be what they really wanted you to do. All right, number 51, reasoning. Explain why the property of equality for exponential equations does not work when b equals 1. Give an answer to justify your answer. Maybe I want to use the example to support what it is that we're talking about. But they're saying when b equals 1, you cannot just set the left side equal to the right side for the thing to work. But the idea behind this is that 1 to any power, I guess I can explain it first. 1 to any power is still 1. 1 raised to any exponent is still 1. So it doesn't matter what your solution is for this to apply. Really the thing is that we can talk about is that 1 is something raised to the 0 power, which is what I want to get more into. But if I had an example that said something like 1 to the 2x plus 5 equals 1 to the, 4x, like that. We don't just say, hey, 2x plus 5 equals 4x. Well, actually, let's do a 3x here. Equals 3x, and then subtract 2x from both sides and get x equals 5. Sure, x equals 5, whatever, but when I substitute 5 into here, I get 1 to this power is 1 to the 15th is 1 to the 15th. I can raise 1 to any power for this thing to work, but the real problem is the whole thing on where we can raise these to the 0 power, right? This can be 8 to the 0 to the 2x plus 5 equals 8 to the 0 to the 3x. Right? Now what happens here is 0 times anything is 0 and 0 times anything is 0. It doesn't matter if these were the same base or not, but you match that, you get 0 equals 0. It's infinitely many solutions in these cases here. That's the idea. You can substitute whatever you want for x, and you'll always get the same set. So infinitely many solutions. Actually, now that I think about it, that might not have been what they were asking. They might not have said 1 on both sides. They maybe just went on one side. So this is one version of the scenario. 1 to a power equals 1 to a power. But what if instead they meant, and my first part's still the same, 1 raised to any exponent is still 1. So what if it said 1 to the 2x plus 5 equals, 16? Problem with this is 1 to any power is still 1. These will never equal each other. This is not an exponential function in and of itself. This is flat at 1. This is flat at 16. So the same kind of problem. I can never raise 1 to a power to get 16. I can't ever raise 1 to any power to get anything other than 1. So it is not a true exponential expression, function. Right? That's also why we can't graph them that way. So there's more than one version that we can talk about. That's among them. And yeah, that's what we got there. Okay. Number 52, thought-provoking. Is it possible for an exponential equation to have two different solutions? If not, explain your reasoning. If so, give an example. Well, very much is. We did some graphing ones with them. So, yes. I got to think about... I want to think about ones that work without having a linear equation, because those are the ones that we saw. In which case, you'd need to have one with more of a vertical stretch. Let me think about one I personally would want to do before moving forward. And I don't know if I'll get integer answers from them, but let me think about it. Okay, at the cost of overthinking things with exponential, things on both sides, let's just do one of the linear ones that we did before. So if we had like 2 to the x on one of them, as long as it hits in two different parts, so... you think of the equation y equals 2 to the x. It intersects at 1 and it doubles, does this over and over. So I just need to make sure that something else hits, before and after. That it hits like here and it hits back there as well. So the slope needs to be a little bit lesser than, like 1 half x, like plus 8 or something like that. It's going to cross up higher and then hit, boom, and it's going to come back down and hit on the other side. So something like that would work. This is linear on this side, but the whole equation as a whole is exponential because exponents dominate this thing. So that's one of them. I mean, we did some of these before where we saw two different points of intersection. So it's weird that they ask that now instead of before. Okay, in exercises 53 to 56, use a graphing calculator to solve the equation. Okay. I want to do this by hand, but these are ones, you're going to learn these ones in... IM2. I think IM2, not IM3. You're going to learn these in IM2 where you'd get the answer where, number 57 actually says use it to find that. Okay. So I'll let number 57 answer it for us as we use the graphing calculator for these ones. So 2 to the x equals the square root of 2. 2 to the x. Hold on, let me clear these. 2 to the x and square root of 2. There we go. So we set them equal like that. Let's get a decent window range here. Actually, these will be pretty small, so I'll just go -5 to 5 like this. Okay. You're going to see 2 to the x here and the square root of 2 there. So where are they intersecting? It's not at 1. I'll tell you that right now. We need the x value. What is it? 0.5. 0.5, also known as 1/2. Probably the better way to actually be mentioning it. Number 54. Square root of 7 equals 7 to the negative x power. Okay? Whoops. Here we go. Square root of 7. And then 7 to the negative x power. Now, if you notice, they have the same base. I mean, they're basing they're working off of the same number base-wise in that representative form. Doesn't mean it's truly the same base. Now, what's that number? Would it make sense that it's -1/2, -0.5? It would. -0.5. Number 55. I wonder how they'd have you lead to the conclusion after all these ones. The first one, for sure, we could talk about it. But number 55, 8 to the x minus 1/2 equals square root of 8. It's at this stage that I believe I should be writing these as 1/2 instead of 0.5s. I mean, I would have anyway, but let's actually officially turn them into that now that they show the 1/2 here. That's a right shift of 1/2 over. So 8 to the x minus 1/2 power here, and here we have square root of 8. Will that fit? Yeah, square root of 8 is 2 point something. So there's this one. Now this is at an integer. This is x equals 1, which might make you go, wait, I was expecting a 1/2 of some sort. Well, you have to remember that this was 8 to the x minus 1/2 power. It was shifted 1/2 to the right. Remember that. And number 56 is square root of 5 equals 5 to the x plus 1 power. Again, they share these 5s together, but there's also a shift, but it's shifted a whole 1 unit over. So I'm actually expecting some sort of decimal version, right? So square root of 5. And then here, 5 to the x plus 1. And I need to write these as they're graphing. Square root of 5. All right, what are we getting here? All right, they look like they're intersecting at -1.5. Agreed? Or -0.5. -1/2. So x is -1/2. All right, those are the 4 solutions. Now, this number 57 says, use the results of exercises 53 to 56 to find the value of x for which a to the x power equals a. So we'll talk about this one here. We basically have to say, what's that matching base? A to the x equals a to what power? Well, if it wasn't made obvious from number 53, looks like it should be 1/2. But does that apply for the rest of them? 2 to the x equals square root of 2. If I did 2 to the 1/2 power, same as square root of 2, does it apply to the rest of them? If I do -1/2 here, 7 to the opposite of -1/2 is 7 to the 1/2. That's square root of 7. That still seems to fit. We talked about this one being a right shift, but if I also do 1 minus 1/2, 8 to the 1/2 is square root of 8. That also fits. And this one here, -1/2 plus 1 is also 1/2, so 5 to the 1/2 is the square root of 5. It looks like this value has to be 1/2. So what are we saying there? Find the value of x. X would have to equal 1/2. What are we saying? X to the 1/2 is the same as square root of x. Fraction exponents, also known as rational exponents, lead to radical, square root, cube root, things like that, radical values, radical functions. Negative exponents lead to fractions. Fractional exponents lead to radicals. Truly bizarre, truly weird. And I like the discovery they do with that, the graphing calculator. I would have told you it, but they did that there. All right, last question. Making an argument. Consider the equation 1 over a to the x power equals b, where a is more than 1 and b is more than 1. Your friend says the value of x will always be negative. Is your friend correct? Explain. I believe your friend is correct here, yes. 1 over a to the x power equals b. A is greater than 1 and b is greater than 1. The fact that a is greater than 1 means it'll, and b is greater than 1 means they'll stay positive for sure. But also, 1 over a number more than 1 means this will be a smaller number, right? A number less than 1. It'll be a fraction. 1/2, 1/5, 1/20, things like that. And b is a number more than 1. B is growing. It's not a fraction. Well, it could be some improper fraction or a decimal, but it's something more than it. Right? The only way for this thing to be possible for a fraction to turn into a non-fraction, like an integer, a bigger number right here, is if we have a negative exponent here. So, yeah, your friend is correct. My friend is correct because negative exponents take the reciprocal of a fraction and turn it into a number greater than 1. Which is what this situation calls for. So I don't know if I'm explaining that best, but my friend is correct with that in mind. That's going to be happening, something like that. Something there. All right, guys. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching. I hope this stuff made some pretty good sense, and if not, I have a few more problems for you to take care of if you'd like to. Different kinds of problems. If you look at the description section down below at the very bottom, you'll find another set of 24 problems where we do a lot more in isolating the exponent term, and I think that that's a good one to talk about as well, because this didn't cover that greatly, but it is still there. The next two sections, I believe, the next section is on geometric sequences, I believe, which that kind of bases things off exponential functions, but also arithmetic sequences of old. If you remember the whole writing the explicit rule and find the 10th term and things like that, but we got to use exponents. And then the next one is on recursively defined sequences, which uses arithmetic sequences as well as geometric sequences. So get ready for those. It might sound a little bit different from what we did from the exponents things before, but that's what this whole chapter is about before we hit statistics and geometry. Guys, thank you so much. Take care. I'm going to see you in the next one.